Welcome to this explainer. Okay, so today we are diving into a genuinely unexpected and frankly fascinating connection. We're looking at the bridge between protein evolution in biology and the absolute cutting edge of AI software development. We so often think of AI as this purely synthetic thing, right? Just a cold world of code and silicone. But the methods we're now using to push AI agents to the next level, they closely mirror how nature itself optimizes complex biological machines. So today, we're exploring an incredible concept called loop engineering. It's basically a framework that bridges the gap between optimizing enzymes in a lab and building autonomous software agents that can literally code themselves.
To understand this, let's look at biology for a second. Researchers optimize enzymes like the TEV protease you're seeing here through a process literally called loop engineering. It's so cool. In a recent study, researchers used deep learning tools combined with experimental directed evolution to construct what they call mutant libraries. They use these to mutate highly flexible loops within the enzyme. By tweaking these loops, specifically loop 1 in the structural model, they organically enhance the enzyme's performance and substrate affinity. That highlighted mutation you see actually expands the substrate binding pocket. It's this relentless, iterative process. You mutate, test the results, select the best performer, and just repeat that until the enzyme functions perfectly.
Now, here is where it gets crazy. Just as biologists engineer these flexible loops to let enzymes evolve and optimize autonomously over successive generations, AI developers are now adopting the exact same framework. We're finally moving away from manually holding the AI's hand all day. Instead, developers are engineering software loops that allow AI agents to test, correct, and optimize themselves over and over again without constant human input. It is literally directed evolution, but for software.
All right, here's our roadmap for today's explainer. The evolution of loops, moving beyond manual prompting, the anatomy of a loop, the 5 core components, designing safe AI loops, and finally, the future system designer. Let's jump right in.
Section 1, the evolution of loops, and why this is such a massive paradigm shift.
To really grasp this shift, we have to look at where we're coming from. For the last couple of years, the standard was single-shot prompting, or maybe linear chains of commands. But honestly, that manual workflow, it has a really hard ceiling. The crucial turning point here is captured perfectly by Boris Cherny, head of Claude Code at Anthropic. He said, "I don't prompt Claude anymore. I have loops running that prompt Claude and figuring out what to do. My job is to write loops." I mean, wow. That is profound. It shows that manually typing back and forth with an AI, reading the output, spotting the error, typing a correction, is no longer the cutting edge. The new meta is building this system that prompts the AI for you.
Moving on to Section 2, beyond manual prompting and putting the agent in the loop. So this transition fundamentally shifts us from a human-in-the-loop bottleneck, where the software is totally dependent on your typing speed and your attention span, to an agent-in-the-loop engine. The AI actually drives the iteration forward entirely on its own, and the foundation of this autonomous engine is something called the REACT pattern. Reason, act, observe, repeat. Think about it kind of like a robot vacuum. A robot vacuum doesn't just drive blind, right? It reasons about the room, it acts by driving forward, it observes when it bumps into your couch, and then it repeats the process to map the space. Software agents now do exactly this, but with code. They reason about a goal, act by executing a step, observe the real-world results like a compiler error, and then repeat that cycle until the task is definitively complete. Let's look at a practical example, automating a creative task, like making YouTube thumbnails. Instead of you sitting there manually tweaking an image prompt a dozen times, you can just engineer a loop. You give the AI a strict 4-point grading rubric, scoring things like visual contrast or relevance to the title. Then, the loop allows the AI to generate images, self-evaluate against that exact rubric, aggressively reject its own bad designs, redo the failures, and then autonomously deliver only the top 3 results to you. Just think about how much time you'd save if you only had to review the final, polished output, instead of managing all those exhausting micro-edits. Section 3. Let's break down the anatomy of a loop, specifically triggers and goals. Okay, if you want to actually build one of these autonomous workflows, you really need to understand the basic anatomy, because without structure, an AI loop is just going to spin out of control and burn through your resources. Every loop relies on 2 fundamental anchors, a trigger and a verifiable goal. The trigger is simply the mechanism that starts the loop. This could be an event, like a new GitHub pull request, or maybe an external data point, like, say, the final whistle of a World Cup match, automatically triggering a loop to update a score tracker app. But the verifiable goal is arguably even more important. That's the highly specific condition that tells the AI, okay, you are finished. And a truly great verifiable goal has to be purely objective. Take this example. All tests in test/auth pass and lint is clean. Boom. That completely eliminates the ambiguity that can trap an AI in an endless cycle of guesswork. If you just tell an AI to make the code better, well, it's going to happily keep tweaking things until the end of time. A binary, objective standard is quite literally the only way a loop knows it's time to clock out and safely terminate itself. Section 4. The 5 core components you need for structuring the machine. To build robust, scalable loops across any platform, there are 5 core primitives you need to know. Engineering leader Adi Osmani outlined how these map almost exactly across major tools today, from Codex to Claude Code. And what that proves is that this isn't just some gimmick for one specific app, it's a universal shift in software architecture. The very first piece is automations. These act as the heartbeat of the loop. They run on a schedule and handle all that tedious discovery work completely autonomously. Picture this. Your loop wakes up every morning to do daily repository triage, summarizing continuous integration failures and hunting down bugs introduced last week, all so you don't have to. It just leaves a neat little report for you without you ever lifting a finger. Next up, we have Worktrees and skills. Look, if you have multiple agents working at once, they're going to step on each other's toes. And if they have no context, they start completely cold every single time. Worktrees solve that first problem by isolating parallel features in separate checkouts. Skills solve the second problem by codifying your project's unique conventions into memory. That means the loop doesn't have to painstakingly rederive your entire project context from absolute zero every single cycle. Number 4, connectors. This is where the magic really happens, because connectors allow the loop to step outside its isolated file system. It breaks the AI out of the sandbox so it can take real action. Connectors let the agent use your existing tools. It can update a linear ticket, hit a staging API, or even ping a Slack channel to let your team know, hey, tests are green and the fix is ready. And that brings us to the 5th component, sub-agents. This is arguably the most critical part for quality control. You absolutely must separate the maker, who writes the code, from the checker, who reviews it. Why? Well, because an AI grading its own homework is incredibly unreliable. The checker sub-agent is your absolute defense against hallucinations making it into production. It catches all those weird logical leaps that the maker agent might try to pass off as a finished product. Which leads us perfectly into Section 5, designing safe AI loops and setting up essential guardrails. Since these loops are running totally unattended, you have to put guardrails in place. Otherwise, you are risking your entire codebase and your API budget. To prevent ruined projects or massive, terrifying token bills, what engineers grimly refer to as token black holes, you have to follow 3 rules. Number 1, set hard stops. Always give the loop a maximum number of rounds or a strict token limit. Number 2, define boundaries. Explicitly tell the AI what it is absolutely not allowed to touch, so it doesn't accidentally delete core files just to get a test to pass. And number 3, like we just talked about, always rely on objective, separated verifiers to check the work. Finally, Section 6, the future system designer. This whole evolution, from manual prompting to loop engineering, it's not just a neat trick. It signals a fundamental change in our entire relationship with software development and problem solving. We are rapidly moving away from being mere prompt operators who micromanage AI toward becoming system designers who architect entire environments for AI to succeed in. So, as we step into this wild new era of agentic workflows, I want to leave you with a question to think about. As these models get more and more capable, will you be the one manually pushing the buttons or the one building the machine? Thanks so much for joining me on this explainer, and I will catch you in the next one.